This video presentation is brought to you by the Pro Mathematics Academy. Welcome back to another video presentation brought to you by the Pro Mathematics Academy. In this video, we'll be looking at how to prove that a function of a certain form is injective or surjective. And if we prove that it is both injective and surjective, then that means that that function is a bijective function, right? So here, we're starting with question number 3 of our tutorial exercise set, which reads, given that a function f maps elements from the set of reals except the number 2 onto the set of reals such that f of x is equal to the reciprocal of x minus 2. Here, we should recognize that we have the set of reals except 2 as our domain, and as our codomain, we have the set of reals. So let's label that. Right. And without further ado, I jump in to ask my first question. All right. My first question here is, how do we prove that a given function is injective? So therefore, how do we prove injectivity? And there are two methods, right? First, we have the horizontal line test, right, which involves using the graph and drawing horizontal lines. Okay, so if you have the graph, you can use the graph, right? So by drawing horizontal lines, if you cut the graph more than once, then we say that it failed the horizontal line test. So when doing the horizontal line test, we need to intercept each y value only once. Okay, so let's make a note of that. Nice. Secondly, we have the f of a equals f of b implies a equals b proof. Okay, while this method is more of an algebraic method. Okay, the horizontal line test is a geometric method and it involves using the graph. So here we don't want to draw any graphs. Okay, well, I don't want to draw any graphs, but if we had the graph, we could use it. All right, so let's jump right into using our f of a equal f of b implies a equal b proof. Okay, so now f of a equals f of b implies that 1 over x minus 2 1 over a minus 2 is equal to 1 over b minus 2, which then implies that a minus 2 is equal to b minus 2, which then implies that a is equal to b minus 2 plus 2, which implies that a is equal to b. Voila. Therefore, we have proven that f of x equals 1 over x minus 2 is an injective function. Right, so the next thing we need to do now is to prove surjectivity. So how do we prove surjectivity? And I only know of one method right now. Okay, so if you know of any other methods, you are free to comment down below. Okay, so we compare the range of f and the codomain of f. All right, so if range of f is equal to the codomain of f, then f is surjective. So usually the question starts off by giving us the codomain. So here we already know that the range, well, the codomain of our function here is equal to the set of real numbers. What is the range? Now f of x equals 1 over x minus 2 can take on many values, both negative values and positive values. Now, looking at this function, there is one value that this function cannot take on. All right? There is one value that this function cannot take on. Now, how do I find that? I'll say let a be a real number in the codomain of f such that a is equal to f of x, right? And this is a standard procedure that we use, okay? So if 1 over x minus 2 is equal to a, this implies that 1 over a is equal to x minus 2. And we can stop here because we see that a is not equal to 0, right? So now we have a contradiction. Since a was supposed to be a member of all real, but here we're saying a cannot be equal to 0. So once we have that contradiction, we now know that there's an element in the codomain that is not in the range, okay? So I'll state that explicitly. So a is an element of the codomain, but not in the range. And so if it's not in the range, therefore the range cannot be equal to the codomain. So f is not surjective. But what step can I take? What step can I take to make this function a bijective function? We already know it's injective, so we just need to make it surjective. So the step that we need to take is we need to remove the number 0 from the codomain. And if we do that, then this new codomain, which does not include 0, will be identical to our range. So that means f should now map from the set of real numbers except 2 onto the set of real numbers except 0. And I hope that's making sense. All right. So moving right along to question number 4. So for question number 4, we're given this function f of x equals modulus of x plus 2, where we're mapping from the set of integers onto the set of natural numbers. So let's go. Injectivity. F of a equals f of b implies that the modulus of a plus 2 is equal to the modulus of b plus 2, which implies that the modulus of a is equal to the modulus of b plus 2 minus 2, which implies that the modulus of a is equal to the modulus of b. Now, a quick question to ask at this point is, modulus of a equals modulus of b. Does this imply a is equal to b? Because if it does, then the proof is over. We know that the function is injective. Okay? So let's put in two numbers. -1, the modulus of -1 equals the modulus of 1 does not imply that -1 is equal to 1. Okay? So I think we've just answered our questions just by plugging in two numbers. Even though we can't plug in numbers to do a proof, we can plug in numbers to do a disproof. So here we're disproving injectivity. Okay? So our conclusion, modulus of A equals modulus of B does not imply A equals B. Therefore, our function modulus of x plus 2 equals f of x is not injective. Okay? So, is there a way we can make this function injective? What is the step that we would need to take in order for this function to be injective? Well, based on what I'm seeing so far, what we would need to do is we would need z plus only or z minus only to be our domain. Okay? So if we have only z plus or z minus, then we could say that this function would become injective. Now I'm interested to see who gets that off the top. Moving right along. So now we want to test for surjectivity. So let A be an element of the codomain. In this case, our codomain is, scroll back up, the set of natural numbers, okay, such that f of x is equal to A. This implies that the modulus of x plus 2 is equal to A, which means that the modulus of x is equal to A minus 2, which means that, hold on, there's a restriction on the modulus of x. The modulus of x must be greater than or equal to 0. So this implies that A minus 2 is greater than or equal to 0, which means that A is greater than or equal to 2. We have a contradiction. We have a contradiction. What is the contradiction? We said that A must be a natural number. Not only must it be a natural number, it can be any natural number. But we have a restriction. We have a restriction that says that A must be greater than or equal to 2. But what if A could be equal to 1? The codomain says A could be equal to 1, but our manipulation here is showing us that A cannot be equal to 1. So since we have a contradiction, therefore, the function modulus of x plus 2 equals f of x is not surjective. But what can I do? Is there a step I can take in order for the range to be equal to the codomain? Here we see that the range is greater than or equal to 2, right? Here we see that the range is greater than or equal to 2. But the codomain says that we need to be greater than or equal to 1. So therefore, if I choose f to go from the set of integers positive onto the set of natural numbers except the number 1, then f will be bijective. Okay? So the range is what we actually solved for here. Okay, and once we choose a new codomain that is identical to the range, then we will have a bijective function. And we are moving right along into our last question, which says that determine by way of a proof whether the following functions are injective and surjective. So we have the second function here, right? F of x equals 5x plus 1 divided by x minus 2, where f is going from the set of reals except the number 2 onto the set of reals except the number 5. Now, injectivity. How do we prove that? F of A equals f of B implies that 5a plus 1 over a minus 2 equals 5b plus 1 over b minus 2. This looks like an A. Let's erase that right properly. Plus 1. Nice. This implies that five a minus 10 plus 10 plus 1 all divided by a minus 2 is equal to 5b plus 10 is equal to 5b minus 10 plus 10 minus plus 1 all divided by b minus 2, which means that 5a minus 10 over a minus 2 plus 11 over a minus 2 is equal to 5b minus 10 over b minus 2 plus 11 over b minus 2 implies that 2, well, not 2, implies that 5 times a minus 2 over a minus 2 plus 11 over a minus 2 is equal to 5 times b minus 2 over b minus 2 plus 11 over b minus 2. This then implies that 5 plus 11 over a minus 2 is equal to 5 plus 11 over b minus 2. This means that 11 over a minus 2 is equal to 11 over b minus 2. This then means that a minus 2 is equal to b minus 2, which means we now have a equals b. Wow. Therefore, the function f of x equals 5x plus 1 over x minus 2 is an injective function. Okay, can we now prove that this function is also surjective? So we know that the codomain of this function is equal to the set of reals except the number 5, right? It was given to us right here. Now, we'll say, okay, take a in the codomain. This means that f of x is equal to a, which now means that 5x plus 1 over x minus 2 is equal to a. Can I manipulate this expression to give me x as the subject of the formula? Let's do that. So let's make x the subject. So 5x plus 1 over x minus 2 equals a implies that 5x plus 1 equals a times x minus 2, which means that 5x plus 1 equals ax minus 2a, which means that 5x minus ax is equal to negative 1 minus 2a. This then means that x times 5 minus a is equal to negative 1 minus 2a divided by a minus 5. A cannot be equal to 5 based on what we're seeing, okay? But this was already accounted for in the codomain. Therefore, range is equal to, what is the range here? The set of real numbers minus the number 5, which is equal to the codomain of f. Thus, f is a bijective function, or f is a bijection. Okay? Awesome.